Hello, I'm Takuya Inoue from the University of Tokyo, Japan. Uh, According to the abstract of this talk, the title was Seeking a Bijection between SPPs and QTCPPs. But in fact, I found the bijection recently. So today's title is A Bijection between SPP and QTCPPs. Uh, this talk is based on the preprint which I submitted to archive yesterday, so it will appear soon. So, um, my, yes, my major is on bijective combinatorics, and for example, in my master thesis, I gave another bijective proof for the operator formula, which was introduced in the last talk. Please explain the background of my research. SPP's symmetric plane functions are very famous class of plane functions, but QTCPP are not so famous, I think, which are introduced by Florian when he studied higher dimensional plane functions. QTCPP means quasi-transpose plane functions. The yes, Florian uh, uh, modify the condition of transpose complementary. Um, QTCPP is quasi-transpose complementary plane functions. Uh, uh, they modify the condition of transpose complementary a bit to generalize it to higher dimension. A plane partition is quasi-transpose complementary if it is transpose complementary except for the entries to it on the diagonal line. So this is the definition. If it's negative, which and they prove the granularity between CP and PPP. There is no bijection, and we construct explicit bijection between them. As a first step of my research, I read the problem with five granularity between further bifoctor among SPP, even SPP, and stable functions and finite stable functions. SPPs is symmetric plane functions, and even SPPs with increase on diagonal line. And this is the example of stable plane function means plane function is shape of the mind. And participative reflection is the state reflection. It will be also not this case our six agrees should be divided to n and what about one of the and yes, yes. Questions? Is that for notation for PhD, it is the set of even the series of cycles is upon doing. This one can be. Okay, I have to speak here. Okay. Yes, so yes, for by this notation, the identity uh, can be good, and so the theorem by Proctor, um, the they prove the equinumerosity between SPPs and parity staircase preimpositions, and even SPPs and staircase preimpositions. The proofs are given using methods from representation theory and by direct computation, and no explicit variation between them is provided there. And it's not related to this talk, but a variation between even SPP and staircase preimposition, sorry, the reference is broken, but by tissues using a symplectic Jirutakan algorithm. And this is also interesting result, but in fact, to construct a variation between SPPs and QTCPPs, we cannot use this construction. For details, I will explain later. This is an outline of our construction. First, we can find simple variation between QTCPPs and parity staircase preimpositions. So by this variation, we can relate the SPP QTCPP variation problem with Proctor's equinumerosity. And in fact, there are two one-to-two-to-S correspondence between SPP and SPP and other set explain function and step explain function. And one-to-two-to-S correspondence means family of variations, which means some good relation between them. I will explain later. And by these relations, the task, the SPP QTCPP variation problem is reduced to the task constructing a compatible variation with S in some statistics. Here, S is a set value function on either SPP and staircase preimpositions. And if we find a good variation, anyway, the task is reduced to the task constructing a good variation between even SPPs and staircase preimpositions. And we found it. I explain the 1-2-2-2-S correspondence. Yes, we construct the following variation. At first, a simple variation between QTCPP and staircase preimpositions. And 1-2-2-S correspondence means these two variations. First, staircase preimposition of size n with upper bound to n plus 1 is in variation to staircase preimposition of size n with upper bound m times 2 to n. And this 2 to n, this direct product can be recognized as this for upper in staircase preimposition only. And in odd case, we can construct a variation between this of this. And um, same relation, there are same relation between SPP and even SPP, where externals are set of variable functions, staircase preimpression, and even SPP. So by these projections, it's sufficient to construct a projection F from between even SPPs and staircase preimpressions together with projection G pi from F pi to F pi. If this picture indicates a case where large n is equal to m, so even case. But odd case is a bit easier. If we have partition f from events ppnm to step ppnm, we can construct a partition between QTCPP and SPP because starting from QTCPP and large M, and go to staircase partition M, and by this correspondence, we can go this distant unions, and by the partition between staircase frame partition and even staircase frame partitions, we can go from here to here, and sorry, here to here. So I'll consider all the kids. So staircase frame partition times to the end, and by it, we can go here. You can see here n times to the end, and the rest we use this one to the x correspondence to go to SPP and to n plus one. So if we have a partition between even SPPs and staircase partitions, and already we construct the following partitions, we can conclude that we have a partition between one QTCP. And for all the M, the situation is a bit hard. We have to construct partitions G pi to unite this M. At this point, unfortunately, this construction does not match this condition because since it is not compatible with the statistics, the number of S. So we had to construct a new partition between them. And we construct it based on the knowledge of non-intersecting paths, the lemma, and calculation of sign sets. And in fact, I already explained before, you can use any bijection. So if you take bijections or think bijection derived from bijections, not through bijection, you can obtain the desired bijection by using safe construction with our method. In the rest of this talk, unfortunately, the time is not enough, so I couldn't the details of construction of these bijections. But there are true bijection between them. So, and in the rest of this talk, I want to explain the construction of F and G pi. But in fact, if we construct F, the construction of G pi will be recovered automatically from the construction. So I focus on the construction of F. First, for staircase preimpressions, we provide a non-intersecting path configuration as this. And is we uh, the path from A1 to A1 to B1 records which entry is uh, at least 6, and 8 from A2 to B2 records which entry is at least 5, and at least 4, at least 3, at least 2, at least 1. And uh, I think uh, many of you know so why this is intersecting lattice path. And in this situation, so we have a bijection from staircase plane partitions of size n with upper bound m to non-intersecting lattice path on gamma prime, gamma prime defined as this from A to B, and applying the algebra lemma, the non-intersecting condition is removed. And in this situation, it is special because the lattice path should included in the area such that x minus y is less than or equal to 2m plus 1. And first, we can use the reflection principle. It can be applied to a path from A to B, and not set of paths originally. If we want to count passes from A to B, which is included in the area x minus y is less than 2m plus 1, then we can we define A prime, which is symmetric to 8 with respect to the line x minus y is equal to 2n plus 2. And the number of paths from A to B in the area x minus y is less than or equal to 2n plus 1 is equal to the number of A to B and the passes from A to B minus the number of passes from A prime to B. And we can provide projective proof for this. If the path intersect with the line x minus 1 is equal to 2n plus 2, then we flip the part of the path before the last intersection. Then if the path intersects the line, we can convert it to the path from A prime to B. And by using algebra lemma and the reflection principle, and staircase plane partition are in bijection to lattice paths with here. First we choose for each m with which are ai or ai prime we use, and after that we think all passes from A or A prime to B. it is a bit difficult. But for example, we choose A1, A2 prime, A3, A4, A5, A6. Then we think passes from A1, A2 prime, A3, A4, A5 to A6 to B1, B2, B3, B4, B5, B6. And the sign is the sign of permutations of passes and uh, according to the biological proof of algorithm. And we consider all choice of A or A prime. And so, for example, in this video, we have two to the six choices of endpoints on A prime side. And this passes were organized with the new combinatorial objects IN that support with the translation of n times 2 to n, and yeah, in some definitions we can describe the Bijection I explained here to this we obtain this formulation. And we do same organization on SPP side. First, we provide a non-intersecting path configuration for symmetric plane partitions, I think which is famous. The plane partition is symmetry this is a line. So and because we have choices of endpoints outside A. In this picture, we have some choices on it. Okay? And we now consider even SPPs, but SPPs, so we should consider the evenness condition. Then first, the SPP is even if the endpoint or passes on A side is described this, and then the SPP is if and only if L2y is equal to L2y minus 1 plus 1 for all I. Therefore, we can obtain M passes with length n by this manipulation. Because for two passes, so these two passes, the endpoint on A side is adjacent, so we reflect this path going to the line and translating them by -1, and then we obtain this path. And at last, concatenate these two paths, we obtain path with length and then situation here and here. So we have three paths with length 6 here. So length 8, so length in Newton, but 2 times of it, which is very similar to staircase plane partition size. So we can relate them. And here is there is also another new index set, JM, which may be related to some perfume, but uh, of course, anyway, we can get this formulation. This is very similar to statistical partial size. And finally, we have to construct a suggestion from IM to JM together with some Kisura bijection to obtain the suggestion. And to complete the construction of F, if um, which completes the construction of the desired bijection from SPP to QTCPP. For details of this part and for details of other part, please see print. As summary, we resolve the bijection problem between SPPs and QTCPPs. And we also resolve the bijection problem between SPPs and partition spring partitions, which has been open for 35 years for proves the university. And future work, the combinatorial sets IM and JM deserve further study. In particular, the structure of JM strongly suggests a connection with Pfaffian evaluations. Yes, the support of JM is key. Foundation of TRIM, such as minimum of sigma 1 increase is less than minimum of sigma 4 sigma 4. So we expect application to cluster Pfaffian formulas. Moreover, the study of the signs generating function of IM and JM present as an interesting direction. And yep. Our methods should extend to other bijection problems, especially those involving reflecting boundaries of Paredes restrictions. And yes. And for responses. And that's all. Thank you.